For 70 years, predicting the weather has been a problem of brute force numerical physics. Meteorologists take current atmospheric observations and feed them into supercomputers designed to solve complex fluid dynamics and thermodynamics equations. To generate a single medium-range ensemble forecast, traditional physics-based models require hours of continuous computation, executing over 100 quadrillion floating-point operations per second. Then, Google DeepMind deployed GraphCast. Instead of running on a massive supercomputing cluster, GraphCast was designed to run on a single Google TPU v4 chip. On that single piece of silicon, it generates a complete 10-day global weather forecast in under 60 seconds. To test its accuracy, researchers pitted it against the European Center for Medium-Range Weather Forecasts, HRES model, widely considered the global gold standard for physics-based forecasting. This chart illustrates the results of that head-to-head benchmark, published in Science in December 2023. Across 1,380 distinct verification targets, GraphCast outperformed the traditional physics model 90% of the time. Huawei's Pangu Weather and the ECMWF's own in-house AI model, AIFS, verified this performance through separate institutional benchmarks. To understand why this works, we have to clear up a major misconception. These AI models are not physics engines. They do not contain a single hand-coded law of thermodynamics. They do not know that mass must be conserved. Instead, they rely entirely on pattern recognition. They map statistical relationships across decades of historical atmospheric data, learning how one weather state transitions into the next. Meteorology is experiencing a structural shift in computation. The heavy lifting has been moved away from deriving physics equations at the moment you need a forecast and front-loaded into pattern mapping during the training phase. Classical numerical weather prediction relies on a spatial grid. The atmosphere is divided into billions of specific points. At each one of these nodes, the system calculates changes in temperature, pressure, and wind using strict fluid dynamics equations. This process is rigid. To predict the weather on day 10, the model must calculate day 1, propagate those exact physical results to the neighboring nodes for day 2, and step forward sequentially. This creates a compounding problem known as chaos. Even microscopic errors in the initial observations multiply through these sequential time steps, causing long-range forecasts to rapidly degrade. AI bypasses this sequential friction entirely, and it does so using a massive repository known as the ERA5 dataset. ERA5 is a highly detailed, three-dimensional historical reconstruction of Earth's atmosphere, logging hourly weather states globally from 1940 to the present day. GraphCast processes this dataset using a graph neural network. Instead of sequential physics, the network treats the atmosphere as a structured data object. Data leaps across the globe via connected nodes, comparing current states with 6 hours ago, instantly outputting the future forecast. By treating the atmosphere as a spatial graph rather than a continuous fluid simulation, the AI sidesteps the computational friction of physics equations, eliminating the bottleneck. This architectural bypass creates a specific window where AI models demonstrate a significant advantage over numerical prediction, the 5 to 10-day medium range. In this window, the AI outperforms traditional models on large-scale upper atmospheric metrics, specifically geopotential height and upper-level wind flow. That upper-level accuracy translates to surface-level impacts, specifically in predicting the paths of tropical cyclones. Take the trajectory of Hurricane Lee in September 2023. 9 days before the storm hit land, GraphCast identified a Nova Scotia landfall. At that same range, the 51-member traditional physics ensemble struggled with high uncertainty, unable to consistently lock on to the correct path. This tracks across multiple models. In 2023, the China Meteorological Administration ran an evaluation of Huawei's Pangu weather model. They found that for Western Pacific typhoons, Pangu weather reduced the mean track error by 12 to 15% compared to their operational physics models. The models excel here because the macro-scale circulation patterns, like the high-pressure ridges that steer cyclones, are deeply embedded in the ERA5 training data. When it comes to large-scale historical atmospheric patterns, data-driven interpolation is currently producing more accurate results than physical extrapolation. However, the system has verified blind spots. The most critical failure in current AI forecasting is the prediction of extreme, localized convection, the kind of intense rainfall that causes immediate flash floods. In benchmarks against the traditional HRES model, top AI systems systematically underestimate 99th percentile precipitation events by 20 to 35%. The root cause of this failure is mathematical. During training, these models are optimized using a metric called mean squared error. Look at this grid layout. If the AI predicts a sharp, intense spike of rainfall, but places it slightly away from where it occurred, the mathematical penalty is massive. To avoid this penalty, the network flattens the intense spike into a wide, shallow dome. Meteorologists call this the blurry problem. The model hedges its output, producing a smooth, safe average rather than risking a highly specific, intense forecast that might be slightly off target. Traditional models do not suffer from this statistical hedging because they are driven by explicit physics parameterizations, allowing them to forecast isolated extremes. Developers are aware of the issue. New generative diffusion models, like GenCast, are being developed to generate probabilistic outputs to specifically combat this blurriness. That right now, the mathematical optimization that makes AI accurate on a global average renders it conservative during life-threatening localized weather events. This brings us to a major professional misconception. AI is not replacing traditional meteorological physics. In fact, every AI weather model operates downstream of classical physics. This workflow demonstrates a process called data assimilation. Before an AI model can generate a forecast, it needs to know what the atmosphere is doing right now. AI cannot process raw satellite or weather balloon readings directly. It relies on traditional numerical physics to translate chaotic real-world observations into a structured starting grid. The second structural limitation is the climate change blind spot. Because current AI is trained on historical data from 1940 to 2017, it struggles to extrapolate novel atmospheric conditions. When a warming planet generates a weather state that does not exist in its training distribution, accuracy drops. This is how modern forecasting centers operate today. Meteorologists haven't abandoned their traditional models. They now use AI outputs as an additional guidance tool, alongside deterministic and ensemble physics projections. The future of the industry is in hybrid architecture. Institutions like the ECMWF are currently working to embed machine learning neural networks directly inside their physical dynamical cores. They want the AI to optimize localized cloud and turbulence parameterizations, while strict physics maintain the overall boundaries. AI forecasting also offers a distinct advantage in socioeconomic access. Running a traditional global forecast requires a supercomputer costing hundreds of millions of dollars. Running an AI forecast requires a standard cloud GPU costing a few dollars an hour. This shift grants lower-income nations access to top-tier medium-range guidance. AI hasn't changed the laws of physics, but it has shifted the computational and financial boundaries of Earth sciences.